Greetings, my friends. Today, I wanted to show you something that I made. I made a capacitor. It's not the best capacitor in the world, but I did this on a whim because I thought it would be interesting to try. Now, if you are not familiar with capacitors, or even if you are, you may find this video interesting. The first thing I'm going to do is to briefly talk about how capacitors are made. Then I'm going to show you a time lapse of me actually making this one. Then we'll go through a couple of steps of analyzing some existing capacitors, and then we're going to analyze this one and see just how effective a capacitor it really is. So, with that, the first thing we need to answer the question about is, or the first question we need to answer is, what are capacitors? Capacitors are charge storage devices. A capacitor will store charge briefly and then can return that charge to a circuit. In some ways, they are somewhat similar to batteries, but it is very important not to confuse them with batteries because although both can store charge, batteries store a huge volume more of energy. Batteries have a vastly higher energy density, and batteries can discharge that energy much more slowly than capacitors. Capacitors can charge very, very quickly, and then they can discharge very, very quickly, but the actual total amounts of energy that they store is almost no application ever going to equal or exceed that of even a relatively small battery. So capacitors are rapid storage devices. They store charge and then they return that charge. As to how they are constructed, capacitors are built out of plates, is what they're usually called, of conductive material. And that conductive material is being connected here to the negative and the positive, although, in many capacitors, those can be reversed. And those plates don't touch. The conductors go to plates, and the plates do not touch. In between the plates is a space, a non-conductive space called the dielectric. Now, the dielectric might be filled with air. You sometimes see those. It might be a very, very thin sheet of plastic or other non-conductive substance. The point of the dielectric is to make sure that the plates are not conducting, but they are close enough for the capacitance to work, for the charge to be stored on the plates in the form of electrons that build up and then can be discharged later. Capacitors can be designed with many, many plates, or they can have few plates, and they can have very large plates, or they can have very small plates. And all of these factors, including how far apart the plates are and what material the dielectric is made of, all of those affect the operational characteristics of the capacitor, including its capacitance. Larger plates, more plate surface area, more plates equaling a total amount of greater surface area means higher capacitance. If the plates are closer together, that will mean higher capacitance. Of course, if the plates are closer together, you have to have very, very fine manufacturing tolerances in order to make sure that they don't conduct, because as soon as they do, then you no longer have a capacitor, you have a really, really big blocky wire. So that, in a nutshell, is how capacitors are made, by having two plates that don't touch each other but can conduct, separated by a non-conductive space called the dielectric. So I realized, after reading a little bit about this, that it would be relatively simple to create something that involved two plates. In this case, I used aluminum foil and wax paper. And what I did was I soldered wires to two strips of aluminum foil, and then I separated those sheets of aluminum foil with wax paper, and then I rolled it all up into this little package, I guess you could say, and that's what we ended up with. So I think you might find it interesting to watch the construction process. So through the magic of editing, we will cut to that, and then I'll come back to this video, and we will continue with some analysis of what capacitors do. we can take advantage of this equation. T equals RC, where T equals time, R equals resistance, and C is capacitance. This allows us to figure out what is the capacitance of something. Now, we know that we can figure out the time it takes to charge, because we can do, oh, see, now I'm blocking the light. We can figure out the time it takes to charge using this oscilloscope, and we know the resistance. So using that, we can actually determine that instead of T equals RC, we could say R is equal to T. I'm sorry, that's wrong. Instead of saying T is equal to RC, we can say C is equal to T divided by R. In other words, we can go capacitance is equal to the resistance divided by the time, or the time divided by the resistance. I'm going to get this right one of these days. I'm going to write it down here so you can see it and there will be no confusion. So T is equal to RC, but also C is equal to T divided by R. That's the one we're going to be looking for here, this second equation. Capacitance is equal to time divided by resistance. So what we need to figure out is, what is the time factor here? But there's one other important element to doing this with a signal generator and an oscilloscope, is that we need to know a bit of math, and this is called the time constant, or tau. I am not going to get into the details of why this is. Just suffice to say that it does exist. And the time constant tau is essentially where E is what we call the time constant in these circuits, is going to be when the amount of time it takes for the charge in the capacitor to get to 63.2% of its full charge. So when we look at this, when we go from no charge to max charge, where is 63.2% on this line between these two lines? That is the amount of time it takes to get there. Oops, I need to stop hitting the probe. The amount of time horizontally it takes to get from one to the other, that is the value that we need in order to calculate the capacitance. I hope I'm not confusing people over much. So in order to do that, using an oscilloscope, what we can do, I'm going to turn the cursors on here. I'm going to switch over to, I only need right now the Y cursors, because what we want to do is figure out what is the difference here. So I'm going to put this on the top, put this line here on the bottom. And if we look here, that tells us that the delta of Y is 1.008 volts. Honestly, it's 1 volt, and I probably just need to move these just a tiny little bit, because this signal generator is actually really accurate. So that's as close to 1 volt as we need to worry about. So 1 volt vertically. So now what we need to know is, I'm going to increase the horizontal a little bit, and we're going to move this so that we can actually see. What I'm going to do, what is 63.2% of 1 volt? 0.632 volts. So I am going to take the top line, and I'm going to drop it to where it says, where delta Y is 632 millivolts. Because we need 63.2% of a volt. So as soon as it is there it is. That point there, where this line crosses the line ascending, that's 63.2% of a volt. And I really got to stop. Every time I hit that, it disturbs the circuit. So now what I want to do is I'm going to turn on the other cursors, and then I'm going to, come on now, stay with me. I'm going to place this one at the start of the curve. I'm going to place this one right at the crossover point. So on the x-axis, I'm measuring time now. So when this cursor line here is crossing this horizontal cursor line, that tells me that on the x-axis, I can look at delta x, and it will tell me 21 microseconds. So knowing that it's 21 microseconds, we can do some calculations. Remember that I said capacitance is equal to time over resistance. So the time is 21 microseconds. Let's say 21 divided by, since a milli is 1,000 and a micro is a million, we'll say divided by 1 million. 21 divided by 100,000, 10,000, 100,000, 1 million. That is going to tell us that it's that. Okay, so that's the amount of time in microseconds. We're going to divide that by 2,200. And that tells us that it is 0.0000001 farads. But since we know if we multiply this by, say, a billion, 100,000, 10,000, 100,000, a million, 10 million, 100 million, 1 billion, 9.54. So I think internally the actual number was a little bit different, but that tells us that this is 9.54 nanofarads. I multiplied it by a billion just to prove that that long set of zeros was a billionth. So now we know that that's 10 nanofarads. 10 nanofarads. And we know that that's 10 nanofarads. It's actually about 9.54 nanofarads, at least if I measured this correctly. But between the tiny little errors in measurement here and other little things that might have been introduced error-wise, we probably are a little further off than we would have been if I'd spent more time dialing this in. But that definitely tells us that we're in the right area, and it shows that the equation absolutely works. So now what we want to try is let's measure this other capacitor, the one that I made. Okay, I have plugged in my homemade capacitor into my test circuit and set up the oscilloscope and signal generator. And I quickly learned while I was doing that the values that we were using before wouldn't work because my capacitor is kind of, well, not exactly the best one ever produced for obvious reasons, because I made it on my table with tinfoil and wax paper. And so what I learned was that when I first set it up, it was clearly acting as a capacitor, but it was nowhere getting near its full charge. I had a very strange looking sort of sawtooth-like wave, which told me it wasn't getting anywhere near full charge before it was discharging. So I removed the 2.2K ohm resistor and I replaced it with a 10 ohm resistor, knowing that that would help it charge more quickly because it wasn't getting enough charge quickly enough to even get to full charge. And then that still didn't work. It was just still producing a distorted wave. So I reduced the frequency from 1,000 hertz down to 5 hertz. So 5 cycles per second in order to give it enough time to build up a charge. And I increased the voltage to 2 volts so I could actually see it properly on the display. So clearly this is a substandard capacitor, but that said, it is acting as a capacitor, which I think is pretty cool for something that I made. I just literally made this thing and it's working. So applying the same rules that we did before, where we're trying to derive what the capacitance is of this thing, when I measured from the bottom of the wave to the top of the wave, it was exactly 2 volts, which is what I wanted it to be. In order to figure out 63% of that, 63.2% of 2 volts is 1.264. In this case, I could only get it to 1.263 because it wouldn't let me actually pick that specific value, but honestly, that's close enough. So then I measured the time value of this thing, and that told me it's 4 milliseconds. And if we do the math on that, 4 divided by 1,000, because a millisecond is 1,000th of a second. And if we divide that by the number of ohms in the circuit, that's 10, we get 0.0004 farads, or 400 microfarads. 400 microfarads. That's actually not bad total capacitance for this thing. It is pretty terrible in that it doesn't charge quickly and it takes forever to discharge, but its total capacitance is 40% of this thing, which is pretty impressive in my opinion for something like I said that I made in 15 minutes on my lab table here. So I made a capacitor, and it actually acts as a capacitor. If I start running here, we can see that it takes a little while to generate the signal, but it is actually generating, it is actually being a capacitor. It's charging and it's discharging. And I think that's pretty darn neat. So I'm looking forward to trying to learn what I did right and what I did wrong in making this so I can improve it. And I'd like to figure out my next steps. Some of the things that I'd like to be able to do is figure out how I can know ahead of time what I'm going to be needing to do to get to certain capacitance values. I don't think I can create ones that are as precisely accurate as, say, a factory built one, but there have to be ways to determine what kind of capacitance you're going to get ahead of time. So I assume there's going to be some more research and some more math in my future, but that's fine because that's fun for some values of fun. So I hope you enjoyed this video of me waxing rhapsodic about this piece of crap capacitor that I just made. But I had fun doing it. I hope you had fun following along and learning a few things with me. If you enjoyed this, please consider subscribing and look forward to future videos where I will talk about other home hobbyist electronic topics and occasionally other things that I find interesting and that I think you might find interesting as well. In the meantime, I look forward to the next time we can sit together and chat, and thank you again for watching. Have a great day.